Hello, friends. Welcome. Last class we discussed about one method of breaking three-phase induction motor. What is that method? You remember? Yeah, regenerative braking. In that case, during the braking process, the energy stored in the motor due to the earlier running was not lost. Instead, it was regenerated in the sense it was recovered and fed back to the supply. Today, we will discuss about the other method, the second method of breaking three-phase induction motor, namely the reverse current braking. It is also called as plugging. What is the method called as? Reverse current braking, RCB, plugging. And the simple schematic of this is this. Can you see here? There is three-phase AC supply. There is three-phase induction motor. In between, there is a block. We can call it as a switching block. What does it do? It reverses the phase sequence. In the case of three-phase induction motor, we know that the phase sequence of the supply three-phase AC is very important. It decides the direction of torque developed and hence the direction of rotation. If we reverse the phase sequence, the torque generated will get reversed. We know about it. So the principle of operation of this method of braking, which is called reverse current braking or plugging, is what? Reversing the phase sequence of the already running induction motor generates opposing motor torque. The torque direction will get a reverse, and hence the torque will oppose the already running motor. As a result, the speed will decrease. The motor is already running. Now I start generating the torque in the opposite direction. Obviously, the speed of the motor will come down. It will result in deceleration. So, for the reversing of the phase sequence, we need to have a mechanism, that is what is shown here in the form of a block diagram. The procedure, what is the procedure? Let us assume that already the three-phase induction motor is running. It is running in the forward direction. We have given proper phase sequence. Now we want to break the motor, and to break the motor we are going for this method, and hence using this method, using the switching circuit, we reverse the phase sequence. RYB, if it is the normal phase sequence, now we will reverse it, RBY. Now for braking purpose, the phase sequence is reversed using suitable switching circuit. It can be a basic mechanical switching circuit, or it can be a switching circuit which is automatic, employing solid state switches like transistors or SCRs. Sorry. Due to the reverse phase sequence, the generated torque will be in the opposite direction, that opposes the forward running. Obviously, there will be decrease in the speed. And when the speed decreases, it becomes 0. When the speed becomes 0, if our intention is to stop the motor, then the supply to the motor is cut off. If we do not cut off the supply, then the torque keeps getting generated. Obviously, the motor continues to run, interestingly, in the reverse direction. And the motor starts running in the reverse direction, gets into an equilibrium operating point, and continues as reverse motor. So this reversing aspect is employed in the applications which need reversal, like to and fro motion. In that case, we can make use of the reversal feature. So that reversal what I refer to is nothing but positive to negative. The speed positive will become the speed negative now. So this method has different features. The very first one is the reverse current braking RCB is the fastest braking among all the methods of braking. In electrical braking we have three types. The first one is regenerative braking, then we have reverse current braking, then we have rheostatic braking. Among all the three, this reverse current braking is the fastest. And it also gives the possibility of a reversal. It gives the possibility of reversal. Our intention may not be just to stop, to reverse. Then the reversal happens here automatically. And the reverse current braking gives holding torque. This is very important. What is that holding torque? It is the braking torque even when the speed is 0. Even when the motor is static, you have the braking torque. Very useful where in the case of uphill operations, when we are going up the gradient, we want to stop. Even when we stop, the braking torque is to be there. In such situations, this comes very handy. It's not that it is a must, it is essential. And in this, the reverse current braking method, the energy loss is more than any other method. Maximum energy loss we have here. And what is the reason? Because here it is not only the stored energy that we are evacuating like in the case of other methods. Instead, we are tackling that head on by another active torque. We are generating a torque and we are opposing the already running motor. That means we keep spending energy. So total energy loss, the stored energy and that we have spent together, the total energy loss becomes more. And another thing is, because we reverse the phase sequence, then at the starting of that braking, the supply voltage and the motor's EMF generated voltage, typically called as motor voltage, motor EMF, those two get additive, they become cumulative. As a result, the current drawn by the motor becomes too high. This is to be kept in mind. The instant we go for RCB, the current drawn will be very high. That possibility is there. If that is to be limited, then we need to do something. How do we limit that? Putting an external resistance in series. Include a resistance in series of such a magnitude which limits the current as per our expectations. So these are the different features of the RCB. Then coming to RCB, the equivalent circuit. Look at this. Focus a little. First is the equivalent circuit corresponding to forward motoring. We know about this. The approximate equivalent circuit with the supply voltage, the stator resistance and reactance, rotor resistance and reactance refer to stator. RS, XS, XR dash, RR dash by S. We have assumed the slip to be S, a normal approximate equivalent circuit. Now, on reversing the phase sequence, when the phase sequence is reversed, the stator rotating magnetic field will be in the opposite direction. When the stator's magnetic field is in the opposite direction, then the slip will become minus omega ms instead of plus omega ms. And then with this equation, if we calculate, the slip is not the slip corresponding to forward motion. Instead, it is the negative sequence now, reverse sequence. Hence, we call it as Sn. It turns out to be 2 minus S. If 2 minus SF, where SF, is the forward slip. Okay, so Sn is 2 minus Sf, and the equivalent circuit for the reverse phase sequence will be the same as the one for forward normal motoring, but with the slip replaced by Sn now, because the phase sequence has reverse. Everything else will be the same. One more possibility of change here is to limit the current. Maybe we add some resistance in the rotor. That value also we should include, of course, refer to the stator. Now, if you look at this equivalent circuit, I can find Is equal to IR dash, hence IR dash as V phase divided by this total impedance. That's where I have shown this IR dash as equal to V phase divided by root of Rs plus Rr dash by Sn whole square plus Xs plus Xr dash whole square. That's how I get IR dash, the current in this circuit. With that, we can find the gross power, we can find the copper loss, we can find the mechanical power developed, which is PM Pg minus Pcu. We know that. And the torque generated is the generated power divided by, or the air gap power divided by omega ms. I can use this equation, calculate this. So look at this analysis. We have started with the basic equivalent circuit, normal forward motoring equivalent circuit. Then we represented the equivalent circuit for the reverse motoring, which we get after the phase sequence reversal, and we can make use of the normal usual equations with the normal slip replaced by the negative phase sequence slip, which we have got as Sn equal to 2 minus Sf. Good. So using that we can do the analysis. Now this operation of braking, that is reverse current braking, can be understood from the omega t characteristic also, the speed torque characteristic also. Look at this, it's a omega t plane, omega m the motor speed, t the torque. It's a 4-quadrant representation, quadrant 1, quadrant 2, quadrant 3, like that we have different quadrants. The first quadrant corresponds to forward motoring, and it's a normal characteristic. Look at this normal characteristic, wherein this is the starting torque. Hope you are catching. And normally the operating point will be somewhere here. I have assumed the operating point to be P. Okay, now we go for plugging, and that we do by phase reversal. On phase reversal, the characteristics gets shifted to negative phase sequence characteristic, which is nothing but this motor characteristic. See here, this is the motor characteristic. The extended portion of this in the second quadrant is this. Hence, the moment we switch over to the other phase sequence, the operating point gets shifted from P to Q, which lies on this characteristic. This is the motor characteristic for the other phase sequence, for the reversed phase sequence. Now, the operating point gets shifted to Q, and then it slides down thus. And you can see we are in the second quadrant. The torque is opposite, negative torque. That's why it's called as braking torque. The speed decreases. The torque, braking torque we have here. And in that process, the speed becomes 0. Even when the speed becomes 0, the braking torque is still there. This is called holding torque. T-hold I have called it as. And left to itself, the motor will continue to operate and it will come to a point S wherein it will reach the equilibrium. We already know the definition of equilibrium. It reaches equilibrium at S and then it starts running as the reverse motor. So the whole thing is from point P, if the supply is kept intact, the shift is to S. P to Q, Q to R to S. It is in that sequence it happens if the supply is maintained. If our intention is to stop the motor, what we will do? When the transition takes place from P to Q, Q to R, we will be monitoring the speed. When the speed becomes 0, we cut off the supply. Hence, the motor will stop here. That means, if supply is cut off at omega m equal to 0, it will be transition from P to Q, Q to R. This is how the torque along with the speed is affected. If our intention is to stop the motor still faster, or we want to control the rate of braking, what we can do? The braking torque we want to change magnitude, and that can be changed by having different curves like this. Are you seeing here? I have shown one more curve. There is one more curve, different curves like this. What are these different curves in the case of a three-phase induction motor? These different curves actually correspond to different rotor resistance. By adding an external resistance in the rotor, changing the magnitude of that, we can have a family of characteristics like this. Then we can jump from one curve to another curve, and in that process we can have a higher braking torque, we can have a lower braking torque, thereby controlling the rate of braking. Are you able to see that? So that's what we can have. By changing external series resistance, the braking current, braking rate can be changed. Something like instead of P to Q, I will jump to Q dash, R dash. This we can do hopping from one curve to another curve. Look at this omega t characteristic once more. Please register what we discussed just now in your mind, which you can elaborate yourself. Good. So next, look at this. This method is having the merits. What are the merits? The method has the first merit, that is, it is the fastest. It is the fastest among all the methods. Why not? Because the energy it is consuming is the maximum. Instead of passive braking, we are having here active braking. We are tackling it head on by generating another torque. That's why it is the fastest. And in this method, we have the reversal possibility, automatic reversal possibility, and more interestingly, this method gives this feature, holding torque is there. Very important feature. That is the merit of this. Actually, we have that as the unique feature of mechanical braking. In electrical braking also, the plugging gives this holding torque. And what are the demerits? The very first demerit is this method is, what is that? Energy loss is very high. And because of that, the efficiency is poor, and since we are losing the energy, economy will be poor, and there will be issues like temperature rise, because all this energy is dissipated in the rotor itself. The temperature rise will be more, affecting the insulation there. That's one thing. Second, another demerit is, if your intention is to stop the motor, then we need to monitor the speed. Some mechanism is required. Monitor the speed. When the speed becomes 0, try to cut off the supply. So we need to have a mechanism of monitoring the speed and cutting off the supply when the speed becomes 0. Otherwise, instead of motor stopping, it starts running in the reverse direction. And one more demerit of this method is the possibility of starting current being very high. What is that current? The current at the very start of the braking being very high, that possibility being very high, we need to control. That we should keep in mind. Okay, so the method is very important from this point of view, holding torque present. Okay, but we will have to keep in mind the other things also, these demerits also. Okay, now let us take up the third method of braking, that is dynamic braking or rheostatic braking. That is dynamic braking or rheostatic braking. Okay, so this method of braking is little involved, the analysis, mathematical analysis there. That's why I will not go into too much of details here, but we will try to figure out what is this method about and how actually the braking is accomplished here. Okay, so first the schematic. We have the three-phase induction motor. When it is motoring mode, we give the three-phase AC supply. It runs as a motor, normal. But when we want to break it, then the supply is cut off, and to the stator windings we connect DC supply. In different modes, there are different possibilities depending on the type of the stator winding, whether it is star or delta. So dynamic braking, three-phase AC input is cut off and a DC source is connected, maybe in this fashion, maybe in this fashion, maybe in this fashion. Each method has its own performance. We will not go into the details. Only thing is, we need to connect a DC source to the stator. I will repeat. Normal motoring, the dynamic braking, three-phase AC cutoff, DC source connected to the stator winding. There are different possibilities. So what is the procedure? Three-phase induction motor is already running normally. Now we want to break it. For that, first the three-phase AC input is cut off, AC input is cut off. Then depending on the stator winding, star or delta, the DC source is connected across the stator winding. The speed will decrease and motor will come to stop. This is the approach, the procedure. And what is the principle of this method? The dynamic braking. The principle of this method of braking is, when the input is cut off, rotor keeps running due to the inertia, the earlier operation. Because of the earlier operation, there is energy stored in it, and because of that, what is that energy? Kinetic energy. Because of that, it continues to run. Hope you understand that. Now, what we are doing, after cutting off the AC supply, we connect a DC source across the stator winding. When we connect AC source three-phase to the stator winding, there will be rotating magnetic field. Now we have cut off that. Rotating magnetic field is not there. Instead, we connect a DC source. When the DC is connected to the stator winding, it sets up a magnetic field, but that magnetic field is stationary. Now imagine a stationary magnetic field is set up. In that, the rotor is running. Rotor is having conductors, rotor conductors. What is this setup? You remember something? What is this setup? Magnetic field. In that, conductors rotating. Generator action, no? Hence, the rotor running in this field results in generator operation. And in the rotor windings, there will be voltage, and since it is closed, there will be current setup, and that current results in the loss, power loss, energy loss. Where from this energy comes? The loss is happening in the form of electric energy, but where from this is coming? It is coming from the stored energy of the rotor. And once it continues to happen, then as the losses continue to happen, then the energy stored in the rotor will go on decreasing. Obviously, the speed will decrease. That is how we get the braking here. And ultimately, the rotor will stop. So what is the principle then? The principle here is after cutting off the supply, we connect a DC motor, DC source, and the machine now becomes a generator. The stored energy mechanically is converted into electrical energy, and that is dissipated in the rotor. The stored energy decreases, the speed decreases. Are you able to appreciate this? And what about the omega t characteristics? The speed torque characteristics. See here, this is a first quadrant plot, normal motoring characteristic, wherein this is T start, and when we disconnect the AC and connect DC, the characteristic will be like this. Can you see this? Omega T characteristic. The torque will be reverse, its generating action, torque will be reverse, and the operating point will jump from P to a point on this, say Q. And with the losses happening, speed will decrease, the torque will also decrease, the braking torque. Ultimately, the machine will come to stop here. The machine will come to stop here. Okay. So now this method, it's little interesting, the analysis, but I will not go into the analysis in detail. We look at the merits and demerits of this dynamic braking. The dynamic braking is very simple and it's economic. Very simple and economic to implement. Economic to implement. Of course, the running economy is not there because there is loss. Running economy is poor. And demerits, this method doesn't have holding torque. When the speed becomes 0, the braking torque also becomes 0. There is no holding torque, the serious disadvantage. And there are losses happening here. Obviously, the efficiency is poor and temperature rise issues are there. They need to be addressed. Temperature rise and hence the effect on the insulation. And because the losses are happening, we have the running economy very poor. This is what I mentioned here. The running economy is very poor, efficiency is very poor. These things are to be kept in mind. Okay. So what are the merits and demerits of this method? It is simple, economic for implementation, but running economy is poor, no holding torque, and because of the losses taking place in the motor, the temperature rise issues will be there. Temperature rise issues will be there. Okay. So among all the three methods till now we have discussed the regenerative method, the reverse current braking method, and the dynamic braking. So what all we saw? We have seen the regenerative braking versus reverse current braking versus the RCB, and then the last one we saw dynamic braking. The three methods what we have seen these methods, the comparison is very important. Can you make a simple table bringing out the comparison in terms of different features, like which is slow, which is fast, which is economic, which has the holding torque, which doesn't have the holding torque. So make that comparison, okay. So we shall stop there. Next class we'll continue. Bye, take care.